Chapter 3 review. All right, so let's get into it. Number 1, E, F, and G are all of the outcomes of a sample space S. If probability E is 0.4, probability of F is 0.25, what is the probability of G? So remember, probability always adds up to 1. So in this example, it's saying that probability of E plus the probability of F plus the probability of G is added up to 1. Probability always adds up to 1. So it's something you need to kind of keep in mind. Now, E, as it's already stated, is 0.4. F is 0.25. So the only question is, what is G if all of this adds up to 1? So just take 1, subtract those values from it, and you get G, which I believe ends up being 0.35. But I'll let you do the math to double check on that one. Number two, let E and F be events in sample space, in a sample space with probability of E being 0.6, probability of F being 0.4, and probability of E union F is 0.7. Find the probability of E given F. Now, yes, probability does add up to 1, but you have to think, in number 1, everything was disjointed. There was no overlap region. In this case, and it wasn't specified in number 1, which is kind of a bad thing. But in number 2, don't assume that every probability or every outcome is disjoint, that it's separate. You know, if you have probability of E and the probability of F, there's a chance that there's some overlap shared region here. So just because 0.6 and 0.4 do add up to 1, we're not accounting for the fact that there might be some values in common between those. It's not really important for this one, but I wanted to say that now because there are some problems later that we might run into, and we just need to keep that in mind. So there's several formulas that we're going to need to remember as we go throughout this chapter. One of the formulas, as we're going to use here, is probability for E given F. So the formula for this, the probability of E given F, is the probability of the intersection between E and F divided by the probability of F. Now, it's only the F is only in the denominator because it's the second value here. It's the part that's after the given. If this was the other way around, if this was F given E, then we would have probability of E on the bottom because E is the second part of this. All right, so keep that in mind. But in this case, F is the second part, so F will be the denominator. So all we need to do is figure out what the intersection is and the probability of F, and we'll be on our way. Now, we already know the probability of F is 0.4. So we know the denominator is 0.4, but we don't know the intersection, at least not yet. Let me create some space here. So there's another formula that we're going to need to use to find the intersection here. That formula is this one. The probability of E union F equals the probability of E plus the probability of F minus probability of the intersection of E and F. Now, what this formula is derived from, and the reason why we use it, is essentially what this is saying is you have the probability of E added with the probability of F. So that's everything within this circle added with everything within this circle, and you subtract the intersection, which is this overlapped region here. If you take that away, because you're counting this twice, when you count it with E once, and then you count that region again. You count that region again when you count F, so you have to take it away once because you essentially counted it twice. So the union, which is all of this collective, is when you add up all of E, all of F, and you take away the region that you counted twice. So that's the reason why this formula exists. But we're going to use it to find the intersection here. I already know that the union is 0.7. So I know that 0.7 is equal to the probability of E, which is 0.6, plus the probability of F, which is 0.4, minus the intersection, and that value I don't know right now. So when I work this out, 0.7 equals 1, 0.6 plus 0.4 is 1, minus x. And when I solve this, x ends up being 0.3, which means that the intersection is 0.3. So putting that back in the problem, the intersection being 0.3, that's my numerator. So this ultimately ends up being 3/4, or you might say 0.75. Either answer works as long as you understand they're both the same. Number 3. So very similar problem, but maybe actually even a little easier, because we are finding the probability of E given F, which means, again, the formula that we need to know the intersection of E and F divided by the probability of F in this case. And the reason that's a little easier is because it tells us the intersection right away. We know the intersection is 0.15, so just plugging that right into the formula over the probability of F, which it also gives us, is 0.4. So that comes out to be 3/8 as a fraction. I'm not sure what the decimal equivalent to that is, but yeah, that's the answer. So it is just formulas, so keep that in mind. Number 4. You can do this without circles, but some people, I think, like to visualize the problem a little bit with the circles, so I'm going to use that here. Super cheap motel. The probability of a room has ants is 0.34. The probability of a room has spiders is 0.21, and the probability of a room has both ants and spiders is 0.12. So we're going to have circle for ants, circle for spiders. Now, both ants and spiders is 0.12. So that's going to be this overlapped region here. That's both ants and spiders is 0.12. Now, ants is 0.34 in total. So if we take the difference between 0.34 and 0.12, that'll be the leftover of ants only. So if you take 0.34 minus 0.12, that is 0.22. So 0.22 probability that it's just ants. 0.12 probability it's both ants and spiders, which gives us a total of 0.34 for ants. Spiders is 0.21. So again, we take the difference between that and 0.12, and I believe that is 0.09. Chance that it's just spiders. Okay, so that kind of at least gives us a visual of the problem. Find the probability of room has ants but not spiders. So ants but not spiders, as we just pointed out, is this 0.22. So 0.22. Find the probability you get a room that is insect-free. So the circles are, of course, the rooms with insects. So if, remember, probability all adds up to 1, well, how much probability is not accounted for yet? So 0.22 is just ants. 0.12 is ants and spiders, and 0.09 is just spiders. So this is the probability of all the insect-infected rooms, which I believe comes out to 0.43. So take the difference between that and 1 minus 0.43. We have our answer of, the probability we get a room that doesn't have any insects in it, which should be 0.57. So 0.57 will be our insect-free room. Number 5, E and F are independent. Probability of E is 0.3, probability of F is 0.45. What's the probability of the union E and F? So there's another formula we haven't mentioned yet, and it only refers to independence. So you can only use this formula when it specifically states in the problem that it's independent. People tend to want to use it more often than that because it seems like a very simple formula, and it is. But again, you can only use this formula when it specifically states independence. So the independent formula says that the intersection of E and F is simply the probability of E times the probability of F. So I know the probability of E is 0.3, and I know the probability of F is 0.45. So just multiplying those together, that gives me the intersection. So the intersection, if I multiply those together, hold on a second, 0.3 times 0.45 is 0.135. Now, the reason that's useful is not the answer, because that's the intersection. The question's asking me the union. I have to still use another formula here to get my answer. So I still need this formula. The probability of E union F equals the probability of E plus the probability of F minus the intersection of E and F. So I found the intersection. I already know E, I already know F. So now I can plug all those in to find the union. So the union is equal to probability of E, which is 0.3, plus probability of F, which is 0.45, minus the intersection, which I found from the independent formula, 0.135. And that total will be my union of E and F. So whatever that comes out to be will be your answer. So number 6, let E and F be events in a sample space with probability of E 0.4, probability of F 0.25. If E and F are disjoint, what is the union? So disjoint means that there's no overlap region. So you can think of it like this. There's two ways you can kind of think of it. Probability of E and the probability of F. When it says it's disjoint, it means that there's no value in the middle here. There's no overlap region. So whatever E is and whatever F is, you add them together to get the union. Another visual representation is simply this. If there is no overlap region, then why even draw one in? All of E with all of F will be the union. So simply, when it's disjointed, we're just going to add these values together, and we don't have to subtract anything from it because there is no overlap region. So the answer is 0.4 plus 0.25, which I believe is 0.65, will be the answer to that problem. So number 7, after a restaurant meal, Susan has coffee with probability 0.7, dessert with probability 0.6, and neither with probability 0.05. What is the probability that she has both coffee and dessert? So I'm going to use circles here. Again, we don't need them, but I think it helps majority of us anyway. So coffee, dessert. So she has coffee with 0.7 probability, but again, you can't just put 0.7 here because we're not sure if how much of that 0.7 is going to be in the middle region shared with dessert. So don't jump to conclusions just yet. Same thing with desserts, 0.6, but don't start putting 0.6 in there yet because you don't know how much of that region is, how much of that 0.6 is in that middle part. Neither with probability 0.05. So remember, probability all adds up to 1. And the most important statement in this question is neither with probability 0.05. If she doesn't have coffee or dessert with a probability of 0.05, that helps me figure out, well, what the probability is that she has either coffee or dessert. Something, some kind of, I guess, meal or coffee dessert at the restaurant. So if she has neither, 5% of the time, then she has one of them 95% of the time. So that is the union of our coffee and dessert. If she has nothing, 0.05, then she has one of these as 0.95% of the time. So that's the most important statement because it doesn't say the union is 0.95, but it sort of does indirectly. The union of, I'm going to use C and D here for coffee and dessert. Union of coffee and dessert is equal to our 0.95. Now, I already know that the probability of coffee is 0.7, plus the probability of dessert, I also just know, is 0.6. And now the question is, what is the overlap region? What is the probability of coffee and dessert? That's the question. What's the probability she has both coffee and dessert? So we're trying to find the intersection here. We're trying to find what's the probability of coffee and dessert. So we simply solve that equation and we get our answer. 0.95 equals 0.7 plus 0.6 minus x. I believe it's 0.35, but I don't remember. I think it's 0.35. But I'll let you guys work it out. But anyway, I hope I was making a little bit of sense when I explained the 0.95 part. That's the key to that problem. If A and B are events with probability of A being 0.65, and this should be probability of B here, equal to 0.4, and probability of A intersect B 0.2, what's the probability of B given A? So again, probability of B given A, our formula will be the intersection of B and A over the probability of A specifically. So the intersection is already given to us, that is 0.2. The probability of A is also already given to us, which is 0.65. So just plug them in and you have your answer. So I believe this is 4/13, and whatever the decimal equivalent to that is. So number 9, another one that's pretty simple to use with our formula. Probability of E union F is given by this formula. E plus F minus the intersection. So I know a couple values here. I know that E is 0.4. I know F is 0.36. And I also know the intersection is 0.13. So what's the probability of the union? Well, simply just work that out and you'll get the union. So 0.4 plus 0.36 minus 0.13, whatever that equates to. Number 10. In a CAI program, the record-keeping routine fails with probability 0.15. The log-off routine fails with probability 0.08, and both fail with probability 0.02. What's the probability that both routines work properly? So again, it's probably easiest with our circles. So this will be our record-keeping routine. This will be our log-off routine circle. So they both fail with probability 0.02. So 0.02 is our middle region. Now we'll take the difference between that and the other probabilities to find out the other parts of these circles. So record keeping fails with 0.15, but we already know that 0.02 is shared with the log off. So take the difference between 0.15 and 0.02, that'll be 0.13. So that gives us the whole record keeping circle. And the log off routine fails at 0.08, but we already know 0.02 of that is in the intersection. So take the difference, 0.08 minus 0.02, be 0.06. Now that's all the probability of them failing, remember. So both routines work properly. I'm trying to figure out what's the number that would go here. Remember, all probability adds up to 1. So 0.13, 0.02 plus 0.06 is 0.21. So 0.21 is all the failures added up. So if you take the difference between 1 and 0.21, that difference gives you that they work properly. 0.21 is the failure rate. So 1 minus 0.21, which equals 0.79, is our success rate. Number 11, in a recent municipal election in Mulberry, 7,000 people voted. Of these, 2,500 people voted for an industrial park, 3,200 people voted for a new school, and 1,800 voted for both. A ballot is selected at random. What is the probability that the votes on these issues on this ballot are both negative? So let's make circles for our votes here. We've got people who vote for a park and people who vote for a school. And of course, the box region will be the people who don't vote for it or for neither of them. So I know that 1,800 people voted for both. So 1,800 is sort of this middle region. 2,500 voted for an industrial park. Now I already know 1,800 of that 2,500 voted for a school as well. So if you take the difference, 2,500 minus 1,800, that is 700, and that is the people who voted for a park and a park only. So when you combined the park only folks with the park and school vote people, that is 2,500 people in total who checked yes on park in some way or another. So 3,200 voted for a school, but again, of that 3,200, we already know 1,800 of them voted for a park as well. So if I want to know just the people who voted for the school, I take the difference, 3,200 minus 1,800, which I believe is 1,400, is the total for people who simply voted for just school. And again, I know that 7,000 people voted in total. So if 7,000 people voted in total, well, I'm going to find the difference between that 7,000 and the people I've already counted here to figure out how many people didn't vote for either of these things. So when you subtract it, 7,000 minus 700 minus 1,800 and minus 1,400, we get our total of people that voted for negative to both of these. People who voted for no park and no school. People who voted who didn't want either of those things. I'll let you do the math on that, but yeah, moving on. Number 12, James Bond must send an important message to Miss Moneypenny. He determines that the probability of success by secret courier is 0.6, by carrier pigeon is 0.15. If the success or failure of each method is independent of the other, find the probability the message will arrive if he sends by both methods. So the key to this problem is finding out the probability of them both failing. It's easier to find out the probability of them both failing than it is to find the probability of one succeeding or the other succeeding or both succeeding, because that's a lot of different things to calculate. But what we're really interested in is all of them together. But if we figure out what the probability is that they both fail, then the difference between that probability and one will be the probability that something succeeded, that some part of the message got through one way or the other. So the key to this as well, it says independent. So it says success, probability of success by secret courier is 0.6, but I'm interested in them failing because that's going to make this problem easier. So if success by courier is 0.6, then fail by courier is 0.4. Also, success by carrier pigeon is 0.15, which means failure by carrier pigeon is 1 minus 0.15, which is 0.85. So these are both the failure. Now, failure is independent. So if I want to find the probability that both fail, I'll call this A and this B just to make things simple. The both fail, A intersect B, which is probability of A failing and B failing. Because it's independent, I can just simply multiply those two together. So that probability of A failing is 0.4 and probability of B failing is 0.85. So if you multiply those together, that's the probability that both of them fail, that the message does not get through at all. So 0.4 times 0.85 is 0.34. Now, again, that's not the answer to my question, because the answer to my question is, what's the probability that something will succeed, that the message will arrive? Well, if it's a 0.34 chance that it doesn't arrive, then that means that the remainder is something did arrive. So 0.66 is the probability that something did arrive, that the message got through one way or the other. Number 13. A tree diagram for a multi-stage experiment is shown below. What is the probability of A? So when it comes to tree diagrams, to remind you how they work, probability, you just multiply the branches together. And then after you multiply all the branches, you add them all up, and it should be a total of 1. But here I'm interested in the probability of A. So A is here on this branch and here on this branch. So I'm going to find those two branches, and I'm going to add them up to get a total probability for A. So take 0.7 and 0.65, multiply them together. 0.7 times 0.65, and you get 0.455. And then take 0.3 with what is also supposed to be 0.65 right there. 0.3 times 0.65, and you get 0.195. So if you add those two probabilities for A together, you get a total probability for A. So plus 0.455, and we get 0.65 for the probability of A. So you multiply the branches together, that applies to it, and then you add those values at the end to get your total for A. Move this down a little bit. A box contains 4 blue and 7 red balls. 3 balls are drawn at random without replacement, and the color of each ball is noted. What is the probability that at least 2 are blue? So I'm going to do this using combination formulas because it's going to be way easier in my mind. So remember probability. So the first thing I want to know is how many combinations are there in total? So there are 11 balls in total, and I'm selecting 3 of them. So the combination of 11 choosing 3 will be my total number of ways. That will be my denominator on my fraction. My numerator will be specifically at least 2 blue balls. So there's a couple ways we can get 2 blue. We can have the combination. We're choosing 3, remember. So we can have 2 blue and 1 red. That's 3 balls in total, and 2 of them are blue. But we could also have all 3 blue with no red balls. These are the ways in which you'd have at least 2 blue balls. Otherwise, you'd have 1 blue and 2 red, which is not applied to this, or 0 blue and 3 red, which is not applied to this. These are the ways you can have 2 of the 3 are blue, or you can have all 3 of them are blue, and that's your at least 2 are blue. So now we find the combinations of these, and we'll add them together. So the combination for 2 blue and 1 red, there are 4 blue to choose from. We're picking 2. And so multiply that with the combination of there are 7 red to choose from, and we're picking 1. So that number plus whatever number I get from the second one here, so combination of 3 blue. So combination of 3 blue, there are 4 blue in total, and I'm picking 3 of them. And I'm not choosing any red, so I don't have to worry about that. So take these values and add them up, and you'll have your numerator, which I think ends up being, I think this ends up being 42, and this one being 4, which makes the numerator 46. And I don't remember what this number was as the denominator, but again, you guys have a calculator, you can figure that out. A pair of dice are tossed. Find the probability that the sum of the 2 dice is 7, given that the sum is odd. So remember that there are 36 ways to roll a die. I talked about that, I think, in chapter 2 or chapter 1, maybe in chapter 2, I don't know. 36 ways in total to roll a die. Now, of those ways, half of them are rolling odd. So that means that there are 18 ways to roll odd on a die. There are 36 ways in total. Half of them are even, half of them are odd. So 18 ways are odd. Now, how many of those ways are a 7? Well, a 7 is a 1 and a 6 and a 1 on a die, a 2 and a 5 and a 2 on a die, or a 3 and a 4, or a 4 and a 3 on a die. So that's 6 ways to roll a 7 out of 18 ways in general to roll an odd. So 6 out of 18, or 1/3, would be our answer for this. A pair of dice are tossed. What is the probability that the sum of the 2 dice is 12, given that doubles are rolled? So the only doubles that exist are rolling a 1 and a 1, which is the sum of a 2. You can roll a 2, which is the sum of 4, a 3 and a 3, which is 6, a 4 and a 4, which is 8, a 5 and a 5, which is 10, or a 6 and a 6, which is 12. So there's only, count them, 6 ways to roll a double. Now, of those ways, how many of them are 12? Well, this is the only way I can roll a 12 on a double. That's one way. There's only one out of the 6 ways to roll a double that one of them is a 12. So 1 in 6 chance I roll a 12, given that I rolled a double. So 2 cards are drawn from a standard deck without replacement. What is the probability both cards are spades? So remember, a deck of cards there's 52 cards in a deck, okay? Of those, there's 13 of each suit. 13 hearts, 13 diamonds, 13 clubs, and 13 spades. And also that there's 4 of each type. There's 4 twos, 4 threes, 4 fours, 4 fives, 4 6. There's 1 for each suit, of course. So keep that in mind. Just if you didn't know what a standard deck of cards held. 4 jacks, 4 queens, 4 kings, etc. So here, what's the probability both cards are spades? So first off, there are 13 spades in a deck out of 52 cards. So the first card I pick, 13 out of 52 chance that it's a spades. Now I multiply that with my second probability. So given I've already picked a spade, there's only 12 spades remaining in this deck, and there's only 51 cards remaining in this deck because I've already picked a spade out. So 13 out of 52 times 12 out of 51 will be our total for picking 2 spades. Number 18, 2 cards are drawn from a standard deck without replacement. What is the probability that the first card is a queen and the second is a heart? Now, there's actually 2 answers to this because it depends if the first card you drew was a queen of hearts or not. So 2 cards are drawn from a standard deck without replacement. All right, so the first card is a queen. There are 4 queens in a deck of cards, and there are 52 cards in total. Now, assuming we didn't choose the queen of hearts, then there would still be 13 hearts in the deck out of 51 cards remaining in the deck. Because remember, I already picked a queen out, so there's already 1 card short, so there's 51 cards left. So that's one option. That could be a total. Or the other way, there's, again, 4 hearts, or I'm sorry, 4 queens out of 52 cards. But let's say I chose the queen of hearts, which means there's only 12 hearts remaining in the deck out of 51 cards. So there's technically 2 answers. It depends if you chose the queen of hearts first or if you chose a queen that wasn't a hearts first. I won't put one like this on the test that has 2 answers, but technically you could argue that this does have 2 answers. Number 19, 2 cards are drawn from a standard deck without replacement. What is the probability that both are black? So blacks are the clubs and the spades, which is half the deck. So 26 out of the 52 cards are black. So the first card being black, 26 out of 52 chance that I pick it, or 1/2 essentially. But assuming I've already picked 1 black card the first time, there are 25 black cards remaining, and there are 51 cards in total remaining. So this will be the second card being black. So multiply those together, and you have your total. So number 20, a store stocks CDs as follows: 60% are brand A, 25% brand B, and the remainder brand X. The store owner knows that 10% of brand A, 20% of brand B, and 10% of brand X are defective. A customer returns a defective CD. Find the probability that it is brand X. So I'm going to set up a tree diagram here because there's a lot of pieces to this, and I think it'll help illustrate the problem a little bit better. So there are 3 types of CDs. There's A, B, and X. Now, these CDs could either work or not work. I want to put W for work and N for not work. I guess I should put D for defective because it says defective in the problem. So it works or it's defective. It works or it's defective, and then X can be it works or it's defective. Now, as far as the ones that work, well, all right, so before I get to that, 60% are brand A. So 60% are brand A, so 0.6 will be our probability for A. 25% are brand B, so that'll be 0.25 for B. And the remainder are brand X. So 0.6, 0.25, that's 0.85. So the remainder, which adds up to 1, must be 0.15. Because all 3 of these should add up to 1. So that's how I can find out what the X value should be, which should be 0.15. Okay, now it's works and don't work. So A, 10% of brand A. So this, hold on. The store owner knows that 10% of brand A are defective. So 10% of brand A are defective. So that means 0.9 of them work, 0.1 of them don't. 20% of brand B are defective. So 0.2 don't work, 0.8 do work. And 10% of brand X are defective. So 0.9 work, 0.1 don't work. Now, it says that a customer returns a defective CD. So we already know our CD is defective. So I want to know what's the probability in total for my defective CDs. So multiply these branches out, and I'm going to use a different color to highlight these branches I'm working with. But this branch here will be our defective for A. So 0.6 times 0.1. So let's work that up. 0.6 times 0.1 is 0.06. So this will be 0.06. That is the probability of CDs in general being defective and A. So now let's work on defective and B. So B and defective, this branch, it's 0.25 times 0.2. So 0.25 times 0.2 is 0.05. And now 0.15, so X brand. X brand defective, multiply those two values together. 0.15 times 0.1, which is 0.015. So if you add these three together, you have the total number of defective CDs, which is 0.125. So this is your total defective. Now it's think of it like if there were 100 CDs, 6 of them would be defective and brand A CDs. 5 of them would be defective and brand B CDs. And then I guess 1.5 of them, or basically 1 or 2 of them, are defective and brand X CDs. So think of it like that. And there are in total 12.5 defective CDs. So how many of those CDs were brand X? Well, brand X was 0.15. So 0.015. This was brand X defective. Oops. This is brand X defective out of the total number of defective. And that is your probability for this. Okay. So whatever that comes out to be. So if you take 0.015 and divide it by 0.125 So 0.015 divided by 0.125 equals 0.12, I guess, I think that's the answer. Assuming my calculator did it right. It might not have, but here's the hoping. I think it's right. Number 21. An urn contains 5 white and 3 red marbles. 2 marbles are selected in succession without replacement. Given that the second marble is white, what is the probability that the first marble is red? So this is taking forever, by the way. So I'm going to draw another tree diagram for this. Okay, so I'm going to choose 2 marbles. My first marble could either be white or it could be red. My second marble could either be white or it could be red. Now the probability is going to be a little different here. So the probability I choose white the first time, there are 8 marbles in total and 5 of them are white. So 5 out of 8 chance that I choose the first one white. There's a 3 in 8 chance the first one is red. Now if I assume I chose a white one the first time, then there's a 4 out of 7 chance I choose white the second time. Because if I picked white the first time, then there's only 4 white remaining, and there's only 7 marbles remaining. So 4 out of 7. And that leaves 3 out of 7 for the red. Because again, if I chose white the first time, there would still be 3 red marbles, and there would be 7 left in total. So let me try to make a clearer picture for you. So let me say that this is, the 5 white marbles, and then the 3 red marbles. So if I chose white first, there's of course 5 and 8 chance. I think we get that. But assuming I choose white the first time, then there's 4 out of 7 total marbles of white the second time, and 3 out of 7 marbles are red for the second draw. But if I assume, moving down to the bottom part of the branch, if I assume I chose a red the first time, so assuming I took out a red, then that leaves a 5, because there's still 5 white marbles here, out of 7 for white, and a 2 out of 7 for red. Just to kind of hopefully make the probabilities a little more clear. So now let's answer the question. That just fills out my tree diagram as far as the probabilities go. But given that the second marble is white, so I'm told that I've picked a second white marble. So I want to find these branches. So that would be this branch, 5/8 times 4/7. So 5/8 times 4/7. In this branch, which will be 3/8 and 5/7. 3/8 times 5/7. This ends up being 20 out of 56, and I'm sure that reduces to something. This ends up being 15 out of 56. All right, so in total, that's, if we add these together, that's 35 out of 56 chance that the second ball I chose was white, or the second marble I chose was white. So basically, if there are 56 times I could choose or 56 different ways to choose marbles, 35 of those ways are white. The second time, at least. Now, given that, all right, so out of the 35 ways, this is so tricky to explain, but there are 35 ways in which the second marble I chose was white. Given that fact, what's the probability that the first marble I chose was red? The first marble I chose was red happened 15 out of those 56 times that I chose a white marble second. So 15 out of the 35. That makes sense. Or in another sense, it's essentially 15 out of 56, which is choosing a red and then white, out of the 35 out of 56 of choosing a white the second time in general, which those do end up ultimately being same as 15 over 35, which equates to 3/7 as a total probability. I know that's confusing, and I know that's hard to get your head wrapped around, but I mean, that's how it works, man. I don't know. It's tricky for sure. Let's wrap this up. So number 22 and 23 are pretty simple. They're just a formula for those. So I'll try to make that quick. The formula is a combination of n choose r times the probability of success to the r power and the probability of failure to the n minus r power. So it's just a matter of plugging in the right numbers. So number 22 was probability exactly 5 successes and 16 repetitions of a Bernoulli process with success probability 0.08. So we have a combination of n being the total number of repetitions, which is 16 in this case, r being exactly how many successes we have, which will be 5 in this case, times the probability of success, which is 0.08, or I'm sorry, just 0.8, to the r power. R again is 5 in this case because we're talking about 5 successes. And then q, people always forget what q is, but q is the opposite of p. So if probability of success is 0.8, then the probability of failure is 0.2. Basically, if there's an 80% chance of working, there's a 20% chance of failing. And that difference is that q value. And so n minus r, that would be 16 minus 5, which I'm just going to go ahead and reduce. 16 minus 5 is 11. So that would just be to the 11th power. So work that all out, and you have your answer. And for number 23, it's the same formula. You have to be a little bit careful, though. We're talking about, 20 class meetings that we're going to. Now, keep in mind that the probability of getting the class is 0.85. What's the probability she misses exactly twice? Now, you have to think about it. It does say twice, but if she misses twice, you got to think, how many times did she actually get the class then? Well, if she missed exactly twice, then she made the class exactly 18 times. So that's the R value here, because R is the number of successes and 0.85 is our probability for that success. So 0.85 probability of success to the R power, which is 18, times the probability of failure, which would be 0.15 in this case, because again, 1 minus 0.85 would be 0.15. So just like I said, if there's an 85% chance of it working, then there's a 15% chance of it not working. And then n minus r would be 20 minus 18. And 20 minus 18 is just 2. So you can just put that to the second power. And that should be your formula worked out. And whatever that value is will be our answer. That's going to be it for this video. I apologize for being so long, but it is what it is. I'll see you chapter 4.